Hello YouTube, XCT here. We are continuing today with a video on getting access to the first client machine on Shinra via phishing. After getting a foothold on the machine, we will escalate privileges and then do some post-exploitation work. Okay, so what are our options at this point? We have Ashleigh, who's still waiting for this HR tool, so if you're going to send her a binary, it's likely that she will execute it. So what kind of binary we're sending? We could just use Sliver to generate a payload for us, exe file, but this will 100% get detected, so there's no point in doing it like that. One way you could try that is likely not going to be detected is if you just write a custom reverse shell, something really simple, and send it over and like hard code the IP and the port to connect back. Usually you shouldn't like have a problem there. And in fact, I have one such a tool here on my GitHub, which is called Arcat. It's basically just an nc.exe clone, which connects back to you. Basically the same functionality. But since it's like custom and in Rust, it's not really going to get detected. You can just also rename the file. So you have Arcat, then you have the IP and the port as part of the file name. This works, but obviously this is really bad OPSEC, right? You're telling them directly who you are. So this is one option, but it's not the option we are actually going to go with here. What we actually want is we want to get a Sliver payload executed. We just can't use the exe generating feature of Sliver. We have to generate shellcode and then write a custom program that loads and executes the shellcode. This way we can basically add AV evasion features and still have the full functionality that Sliver provides. So I switched to my Windows VM here to show you the payload I actually used on the lab. It's not like the perfect thing, just an example of what you can do. And originally I wanted to show like the evolution of shellcode loaders and why you use certain techniques but can't use other anymore. But honestly, I think YouTube isn't the right place for that. Maybe I'll do a separate video for like Patreon or something like that, but not at the moment. For now, we just go over the payload here and I'll explain it a bit. So the first part here in main is just a sleep. It's sleeping for 5 seconds and it's measuring how much time has actually passed. The simple reason for this one is that some sandbox solutions will run your payload and then fast forward certain functions, like for example, the sleep function. So they can analyze your payload faster, right? But we can actually detect if the sleep function has been fast forwarded by just checking how much time actually went by. And if it has been manipulated, we can just exit here, right? So this is all I'm checking here. And if this hasn't been the case, we really spend some time sleeping. We go to this download and execute method here. So let's go here. So the first thing I'm doing here is I'm creating a socket, basically using sockets to make an HTTP request to my machine. So you can see the IP, the port, it's connecting to my machine. And then I'm just building like a string for an HTTP request here by hand. And here sending the actual request. And then I'm just receiving everything that comes back. The only thing to pay attention for here is that this will also include like the HTTP header. So we have to parse it out. And I'm just looking for these line breaks here basically and then split it so I only have the data and not like the HTTP header, right? So at this point, we actually have the shellcode loaded from our remote machine. And you might wonder why I'm doing it like that. Why am I loading the shellcode from my machine and not just embedded in the binary? Well, one reason is that Sliver shellcode is just huge. It can be like 10 to 15, 17 megabytes. So if you actually want to include it, you can do it. But Visual Studio doesn't really like really large array buffers or something like that. And also, like, if you think about it, if you put the shellcode just here and then the file gets compiled, lands on disk on a target, it's pretty easy for an AV to just scan the file and find your shellcode and flag it as malicious, right? So I think it's a good idea to like load the shellcode remotely. Let's continue. And in the next line, you can basically see another step that's being done, which is decrypting the shellcode. So what I'm going to do is I'm going to generate shellcode with Sliver. And then I'm running a Python script that will encrypt the shellcode with AES. And exactly with this key and IV. So I'm encrypting it and then using this payload to retrieve the encrypted file and then decrypt it on the fly. Again, the advantage of doing this is that if you request a shellcode over the network, like if you inspect the traffic, you can't really see anything except encrypted randomly looking blob, right? So at this point, we have the decrypted shellcode here. And then we are going to actually trying to run it. The way I'm doing this is, first I'm creating a process, which is Notepad. You can basically start any process you like. This is just like a sacrificial process. We're going to start it and then inject our real shellcode into it. A few considerations here, basically. Like usually you would like want to pick a process that actually does the things normally that you are intending to do with your shellcode. What do I mean by that? For example, if your shellcode is doing like HTTP requests, it makes sense to inject into a binary that also normally does HTTP requests, just to not like draw too much attention to it, right? Notepad, for example, isn't the best example because usually I would guess Notepad isn't really doing HTTP requests. So if it suddenly starts doing them, something is wrong, right? But I leave it to you to find like a process that leans more naturally into like what our shellcode is doing. You could, for example, inject into a browser if you want to. Okay, so the only two other things worth mentioning here is we're calling create process A to create the process, and we're providing extended startup information here. And we do this for the sole reason that we want to block, basically we want to provide a policy that blocks any non-Microsoft binaries or non-Microsoft DLLs to be loaded into the process. And we can do this with this policy and update proc thread attribute here. And the reason is basically that we want to avoid NAV just loading additional DLLs or something into our Notepad process here. So this is one way you can block it out. Other than that, the second flag here is also interesting, create suspended. This means that this process is now, after creation, not running. It's basically waiting for us until we tell it to run. And you will see a bit later why we're doing that. Now we need to allocate actually memory inside this Notepad process that can hold our shellcode. Usually you would use virtual alloc x. Another way is virtual alloc x numa. That's just another function that's like for, I think if you have like multiple CPUs or something like that, or multiple cores and want to decide on which one to run it. I'm not 100% sure. It's just, I guess, a bit more rare function with the purpose of being a bit less suspicious. But you can do really whatever you want here. And we're allocating memory with the size of our shellcode. And we are allocating it with read-write permissions. Note that there's no execute here, which would also be suspicious. Well, because usually memory is either read-writable or read-executable. And usually it's not both at the same time. So we are trying to like not break that. Okay, now we have our memory allocated in the remote process, and we want to write our shellcode there. So we can use nt-write virtual memory to write our shellcode into this remote buffer. You might ask yourself, why not use write process memory, which would be like the normal way to do it. But there's actually a reason for that. So for an example, let's take this graphic here I found on Google. It's just an example with create file, but the same would be true for like write process memory, right? So the way that normally works is that you call a Windows API, and this API is usually in some DLL, for example, here in kernel32.dll. And you would call a function here in kernel32, which then in turn calls another function, which is prefixed with nt in ntdll.dll. And then ntdll will actually execute a syscall into the kernel to do like whatever functionality you need. EDRs and AV companies know that, so they basically hook into these DLLs. So if you do it normally, like you call your functionality in kernel32, the EDR will have like its own method there that just looks at what you give it, what parameters you provided and so on, and then calls the original method. So it basically hooks all of them. And the same DDR basically can do with ntdll. Even though you're not supposed to call it directly, it can basically check here as well and can basically hook it, like place its own function, analyze the parameters, and then call the original. It can do it at both places, like I mentioned. So calling something from kernel32 is not too safe for us. It will probably be hooked. Calling something from ntdll is probably also not going to be the best idea. So let's see what I did here. So I'm calling nt-write virtual memory. And from the name, you could think that's actually residing in ntdll and is hooked. But it's actually not true here. So I'm using a project here called syswhisperer 3. There's 2 and 3, and basically 3 is just like an extended version of it. And what this is doing is it's basically generating headers and assembly files that implement the same stuff that you would find in NTDLL. Like you basically call a function that does the syscall into the kernel, but you don't call it in NTDLL, you call it in your own program. You basically have the same code like NTDLL has, right? And we can see that here in, this is a good example here. You have, for example, ntcreate process here in assembly, and you see it ends with a syscall instruction. So this is basically the code you would find normally in NTDLL that does the actual syscall. This is just in simple terms, right? There's a lot more actually going on to make it work. But what we achieve here is a technique called direct syscalls. We don't have to use NTDLL at all. We can just use this code to make a direct syscall. There are also like other options. There's also a technique called indirect syscalls, but we're not going to go over that one here. Just know that SysWhisperer 3 also supports it. And it's a technique that is even a bit more advanced than this one. There was this great talk here from last year, EDR Evasion Primer for Red Teamers. And here you get a nice overview on how this looks currently, right? You basically have certain levels of what you can do to evade the AV or the EDR here. Basically, the first one is doing nothing and green is detected. So doing nothing is bad, right? Everything gets detected. You do the sandbox evasion. That's, for example, the sleep, but also other things still pretty much detected. You can do something called unhooking. You can try to remove the hooks from NTDLL or bring your own NTDLL and load it into memory. Then you have an unhooked copy. Still a lot of green here. Some cases are not detected. And then you have direct syscalls. This is the one we are using, or I'm using for this payload here specifically. You can see it's kind of a mix, detected and undetected. So it's not the best way to do it. And note that they always have like an EXE or DLL example here. And the difference is what we are doing here is we are sending an EXE to Ashleigh, right? And she is supposed to click it. But we could also have a payload that just places a DLL in some directory. Then when some benign app is running, basically force it to load this DLL just by either overwriting its 16.1 or just placing one that doesn't exist but is basically loaded by the program. Okay, and the next level here basically, like I mentioned, is indirect syscalls. This is like one level above it. You can also do that with SysWhisperer. The difference between direct syscalls and indirect syscalls is basically that on direct syscalls, we implement the assembly to, do the syscall. And with indirect syscalls, we are calling into NTDLL, but we're not only calling the functions, we are calling just snippets that are enough for us to actually call the syscalls. So, but with indirect syscalls, we don't have any syscall instructions in our binary because we reuse existing ones without calling the normal NTDLL functions themselves. So let's continue with our payload here. We used anti-write virtual memory to write our X-ray shellcode to the Notepad process into the buffer we allocated in the step before here, right? Now I'm changing the memory protections back with anti-protect virtual memory, which is the direct syscall variant of virtual protect. And this gives us the read permission, execute read permission on the buffer. So this is like code would normally look. We don't want it to be writable at the moment we execute it because that would look a bit suspicious. And remember, our Notepad process is still suspended. So why did we do that? Because we are going to queue an APC. We are telling it to, when the next time comes that this thread is being executed, and this time will come when we resume it here, we're telling it to first run our APC, which is our shellcode. And this technique is called early bird injection. You can read it up if you want to. Essentially, it just means when the Notepad process is resuming, it will call our shellcode first. This might be a bit more complicated than just calling create remote thread, but the point is that we want to have it a bit less suspicious. These are functions that are basically used more rarely than create remote thread, so you could be unlucky that this one is actually not detected by the particular AV you're testing against. There are many other techniques, and in fact there are repositories just dedicated to listing all the different techniques you can execute shellcode. This is just how I'm doing it here. So to summarize, we're sleeping a bit. We are counting if we really slept or if someone basically manipulated our sleep function. Then we call download and execute, which is here. It's creating a socket. It's basically doing a web request to our machine, retrieving our hosted shellcode here. It's then decrypting it with AES. It's then creating a notepad process that blocks non-Microsoft binaries being loaded into it. And then it's allocating memory in the remote process. It's writing to it. It's changing the protections to read execute. And then it's doing the early bird injection. And this will then lead to our shellcode being executed. So I hope this made somewhat sense. Like I said, I don't want to go into too much detail here because you could do a whole course just about like how to craft a proper payload. For now, I'm going to compile it, transfer it over to my machine, and then we continue. All right, I'm back on my Kali VM. I transferred over the binary, and now we have to do some work in Sliver. First, we have to actually generate our shellcode, right? Going to generate a beacon like this. Generate beacon. I'm going to use mutual TLS, my IP, port, Windows, 64-bit, and the format is supposed to be shellcode. So let's do that. And this is always taking a bit of time because it's actually compiling it. All right, it's built. It's asking us if you want to encode it with shikataganai, but I'm not going to do it. And here we go. We have our raw shellcode. One additional thing we want to do, remember we are decrypting it, so we have to encrypt it. And I just wrote a simple Python script to do that. Just calling it here with the shellcode. Actually, let's go to the web directory and then we can call it. Yeah, it's basically the simple script with the file name, the key, and the IV. So let's do that. And now it has written a binary called xcity.bin. So this was the original shellcode, and this is the encrypted one. And you can see that the Sliver generated one is actually huge. If you wanted to have it a bit smaller, you can skip the symbol obfuscation step. There's a -- skip symbols flag in Sliver. And I think it will be about half the size. But it's really up to you. For me, it doesn't really matter because I load it remotely. So I don't really care if it's 10 MB or 20. But still, it's a lot. If you compare it to like other C2 frameworks, it could be like only 1 megabyte or even less, right? So we have our encrypted shellcode here. What else do we need to do? Well, we need to start a listener. So let's see. We have our listener here. We have our shellcode. We encrypted it. Now it's actually the moment of truth, and we are going to send it. I logged into roundcube here as William.Davis, which was the user Ashley was requesting the tool from. So let's compose an email here to Ashley. HR tool here is for best William. And now we need to attach the file. Here we have our hr.exe, which is 1.2 megabytes. You also have to pay attention that it doesn't get too big because mail server is actually restricting it to 2 megabytes. So it has to be below that. That's just another reason why we can't use a Sliver binary directly, even if it would get past the AV. It would just be too big, right? So let's send this and hope that it works. And you can see that we actually get a request on our web server. So Ashley must have executed the binary, and this is our shellcode that was being loaded here. Nothing in Sliver yet, so we have to hope that it actually works. And here we go, we get a beacon. It took a while, it has to download the 20 megabytes shellcode. But if we now do beacons, we actually have one on the target. All right, so what's a beacon really? And what's the difference between a session and a beacon? Because Sliver knows both of these. So we can do like sessions and we can do beacons. And the difference is that beacons run asynchronously on the client, on the victim, and they sleep the majority of the time. So they will sleep like, I don't know, let's say 20 seconds, and then look if there are any commands to be executed, do it, send back the results, and then sleep again. And this is less suspicious, but it's also like if you want to record a video, really annoying because you have to wait a long time. But like for a real red team operation or pen test or something like that, this is definitely the more OPSEC way to do it. But we can actually change for now from beacon to session mode. And if we look at help here, there's an interactive command. So what you do is you use the beacon. This means like switch into the context of the beacon, and then you do interactive. And then the beacon is tasked with something. This is what I meant, basically. Now it has a task running to open an interactive session, and it will do that when it's time to execute again, because now it's sleeping, right? So we have to wait until it's actually time to do it, and then we should get a session. And here we go, we got our session. If we do sessions now, it's listed here, and we can do use again to switch into the context of our session. And you can see Sliver is doing like red for sessions and blue for beacons. So now that we have our session, what kind of stuff can we do, or do we want to do? First, we want to get some situational awareness. So the first thing I want to do here is take a screenshot to just see if the user is currently doing anything. Let's take that one here. And you can see that the user actually has a poster node on his desktop, which has credentials. So we're going to write this one down. You could also like find the sticky notes database in the user folder. But I think it's always like a good idea to just take a screenshot and see what the user is actually doing, and you might be able to see some interesting things. All right, now we got credentials. What can we do with them? Well, before actually using them, I want to show how you can do like normal enumeration on the box now, an OPSEC, kind of OPSEC safe way. So the feature I mentioned in the beginning is called execute assembly. This will basically load your .NET program from your Kali machine and execute it on the target. And it's not going to write to disk or anything. It's just going to execute, well, the assembly from memory. So that's very useful. Normally what this would do is it would start a sacrificial process, something like, I don't know, another notepad, for example, and inject it into there and then load it from there. This is kind of noisy because, well, we have notepad spawning notepad in this case, which is kind of weird, right? So there's also an option to do it in process. So it will just load it inside our beacon without like spawning a new process for it. And just as an example, let's do execute assembly. So -i is in process and -e is ETW bypass. ETW means event tracing for Windows. I don't want to go into detail what this one is doing at the moment, so we're just going to use the flag and maybe come to it later on. And then just the assembly on our box you want to execute. Just want to show Rubius here. Rubius is on this path on my box, and I want to use Rubius klist to like list the different tickets. And you can see it executed. It didn't really make any problems. There's no detection. And we get the normal output from like Rubius here, right? So this is like a really good way to enumerate. So what kind of programs you want to run? Well, really depends on how you want to enumerate. Maybe you have like a favorite script or something. One thing you can do is run seatbelt, which has like a lot of output. You would do it like this. Let me see. Oh yeah, for seatbelt actually, we can run it like this, but then we have to provide the full path in our box and we have to compile it. Or we can use seatbelt, which is already included in the Armory, right? And if we go up a bit, remember in the first video I did an Armory install all. So we got all these programs here already like pre-compiled and can just use them. And you can see seatbelt is one of them. Actually Ruby is too, so it's up to you which one you want to use. I guess compiling it yourself is the safer option. Let's run that one as well. Seatbelt usually takes quite a while to execute and gives you a ton of output. So you really have to put in some time to like go through everything, see if there's anything interesting in there. I'm not like going to scroll through the whole output here, but I just wanted to show you that this is one of the enumeration scripts you can run here without like taking a big risk because you execute it as an assembly. So yeah, we could basically scroll up for minutes here, but I'm not going to do it. But you get like a real good picture here from what's going on. Other things you can do is you can change directories. So to see here, list directories. This is not like a direct interactive shell, but it's close enough. Like we can look around the file system, we can download and upload files. So it's really useful for us. So another thing I want to show you is that you can get a real interactive shell here if you want to, but this is actually a risky move. It can kill your beacon and EDRs might detect it. And most likely will. I just want to show you how this actually works here. So what we can do is we can use the shell command and then tell it which like binary to use for the shell, which is CMD in this case. So let me run this. And in this case, it actually worked. Doesn't seem like we got killed right away. And then you have a normal shell. You can do that, but it's even warning us here, right? It's a risky move. So let's go with the tool directory here, where we can put stuff. So this one is still empty. Why am I going to Windows Tasks? Well, it's one of the directories that usually exempt from app locker. And we do have app locker on the machine. I think seatbelt output would have shown that. We can also do it manually later on. But if you have app locker, usually, like if it's just the default rules, Windows Task is a safe place to put stuff. What do we want to do? Well, we want to download our HR tool once again from PowerShell. And I'm just going to use the interactive shell here, but you can also do it from the session, no problem. There's an upload and download command. So let's do it like this. Just invoke web request and save our HR tool here once again. Because remember, we found the credentials of the dev user, and what we really want to do is we want to get another session as the dev user. So I put the HR tool here once again, and now we have to, basically find a way to run it as the dev user. Let's exit this one first, because we don't really need it right now. And usually this shell hangs here if you type exit, and you want to do Control-D to basically get rid of that, get back into the session without quitting the client. That's just a quirk of Sliver, I guess. So what we really want to do is this. We want to use runIs, which is a built-in command from Sliver, and we want to give it the credentials that we found on the post-it on desktop, right? And then we want to run the HR binary. And you will see that this actually gives access denied. And this is a pretty tricky error because it's definitely there. It's not the AV blocking it, but it's still access denied. The reason this is happening, and I'm not entirely sure why that's the case, maybe someone can write in the comments, is that we uploaded the binary with Ashleighs, but are trying to execute it with runIs as dev. And this is actually failing. But if we upload the binary as dev and then execute it, there's no problem. So there seems to be some kind of mechanism there that is preventing to run a binary that's was basically uploaded by a different user. I'm not entirely sure which functionality this is, so if you know, please let me know. So how do we get around this? Well, we have to upload the binary with the dev user. Let's get back to our normal shell here first. So we're going to do it like that again. We are on a normal shell. Let's do PowerShell again. Then go to Windows Tasks. All right, so now basically what we have to do is we have to get a shell as the dev user, upload the binary, and then execute it. So we can't upload it as this user that we have right now. I'm going to do another web request here to grab a tool. It's called runIs, and a C# program that basically implements the runIs command with various different techniques. Here we go. And now what we can do is we can call this with the credentials we have, like this, dev and password. We can call cmd.exe and redirect it to our machine. So this is basically just like a netcat shell. Let's open a listener here. And then we should be able to get a shell as dev here. So let's see, who am I all? Also, maybe a comment to who am I. This is also something that will trigger detections because usually admins know who they are, so they don't really have to use it. So you want to avoid it, like if you want to be stealthy. And of course, just to say it again, using these direct shells like here, I'm just doing it here to show why this isn't working. Usually you wouldn't do that. You would try to do everything from the session or even better from the beacon. Okay, so we are now this dev user, and we can see that this user has a few interesting permissions. We have the SE load driver privilege, so we might be able to load a driver. That's interesting, but writing a driver isn't so easy, so maybe there's another way. And we have the SE debug privilege. And the SE debug privilege essentially allows you to open a handle to any process on the system. Also, like useful handles like from the WinLocker process that is running as system. So essentially you have access to any process. And there are two ways to exploit this basically. One way is you can basically use some magic and make a child process of a system process and then inherit the permissions and basically be a system process as well. There's a POC for that, I'll show it later. Or you can just inject shellcode into a system process and then it will run a system as well. So for the first variant, there's this POC here by Daemon Core. And basically he's doing the reparenting thing I talked about. So let's go down a bit. Just quickly, he has this create process from handle function. And it's basically creating a child of a system process and therefore becomes system as well. Let's see if we can find it easily here. Yeah, he's basically spawning cmd.exe with extended startup info. And the info is basically created here with proc thread attributes, proc thread attribute parent process. And this is set to the privileged process. So this is one way you can do it. And since it's C#, you could just execute assembly it and be done. That's a very nice way. But I'm actually going to do something custom here. So a while back, I've written this tool here called adopt. And the original purpose is to, if you're in a situation that you are on session 0, you connect with Vulnlab to a machine, for example, and the same user you're connecting with already has a session on the box that's not in session 0. You can use this to get into session 1 and basically escape the session 0 isolation. It's not too important what this is doing. The important bit for our situation is how this is basically working underneath. What I'm doing here is I'm basically taking a process that has shell execute already in it. It's already imported it. And then I'm calling it with the string path of our choice. So the original use case was to inject into Explorer, because Explorer is a binary that has shell execute imported, and then give it a string of the binary we want to execute. This will basically force Explorer to execute our binary, and therefore we could escape the isolation here. But since we have the SE debug privilege, we could also just, instead of Explorer, use something that's already running a system. And if it has shell execute imported as well, we can just run any binary as system. I hope that makes sense. If not, please check out this repo and look a bit through the source. All right, so let's use that one. Just going to go to Windows Task here again. So now we have these two tools here. Let's pull the adopt one as well over. So first, let's switch to PowerShell. And then I'm going to download the HR tool once again, this time called Google Update. It doesn't really matter. Remember hr.exe we uploaded with the other user. So it's not working for us. So we have to upload another one. Okay, that worked. And I'm also going to upload the adopt.exe from my box. I already have it compiled. And I'm going to call it Google Update v2.exe. All right, now we got both of them here. And now I'm just going to run adopt, just like on the web page, right? This is adopt.exe, just with another name. And I'm injecting into a system process that has shell execute. And you have to do a bit of like research to find which one that is. Maybe there are multiple ways, but one of them is the VM tools daemon, which is running a system and has shell execute. So it's perfect for us. We just force VM tools to execute our Google Update.exe, which is just the HR tool with another name, right? Yes, now it actually worked. It found the process ID of VM tools D. It found where shell execute is in memory. It's written the path into the remote binary. And this is really just this string here. And then it's basically calling shell execute in the remote binary with this path as an argument, and it will spawn the binary for us. Yeah, here we get the hit on our web server, and here we have our beacon, but we are still in our interactive shell. If we exit it, Control D, and then do beacons, and we actually have a system beacon. So this worked. Now that we are system, we want to do some post-exploitation work. For example, we want to do Rubius again with triage to see if there are like any interesting Kerberos tickets around. Again with in-process execution. And there doesn't seem to be anything interesting here. So let's continue. One thing we want to do, let's do PS here, is we want to dump the LSAS process just to see if there are any credentials in memory that we can use. So we have to remember the process ID here. So I'm going to use nanodump here. First, let's switch to a directory where we can put it, for example, Windows tasks again. Or we have to do it actually like this. Sliver doesn't like it. Our directory here. And we also should like delete the tools here. Definitely don't want to keep them around. But for now, let's do the dump. So nanodump 688. Give it a name. And now it's executing nanodump. Let's see, it's telling us we are not allowed to do it. Let's see. Yeah, so I made a mistake here. I tried to run it from our session we have as Ashleigh, but of course we have to use the system one, right? So let's use that one. Actually, let's also make it interactive, just for the sake of the video. Right, we got our session, so let's use that one. Check, we are still in the Windows task directory, that's good. And we want to do our nanodump command again. So let's just repeat that, this time from system. See if it's correct. Yes. And now it actually did the dump. If we do ls, it should be here. Yes, here it is. Let's download the file. Let's just download it to temp in our box. Okay, we got the file, and now just like it told us here, we can use PyPyCats to, well, pass the dump. Let's do it like that. And here we go. We got a lot of interesting output. So this is the machine account hash here. Let's see if we find anything else that's interesting. Here we go. Here's Ashleigh Lewis, also interesting. We have the NT hash and the SHA-1 of her. And that's it. Oh, well, there's also the dev account here, but we already have that one. So there isn't really too much interesting stuff we get here, but it's still useful to do because you never know, right? And one last thing I'm going to do is just snoop a bit around the file system. So let's go to C users. Just do an ls. And if we look at these users, you can see that there's one user here, which is a bit unusual. This is Linda Perry. We haven't heard anything about this user yet. So let's go to her directory. Do an ls again. And you can see, basically, you would look like through all the folders here, right? See if you can find anything interesting. But particularly interesting here is that there's a .ssh folder. If we go there and list them, we can see that there's a private key here and public key file. And maybe these can be used on some other machine in the lab. So let's download these. Just going to download them to temp again, just like this. All right. And then let's see the public key. Maybe it tells us where it's going to connect. And it has @prof here. So maybe there's a machine called prof. We can cross-check with the Bloodhound data we have. And we can try to connect there. This is something we are going to do in the next video. For now, that's basically it, what I wanted to show here. Just to summarize, we sent a payload, we got a shell. We did some enumeration work, found credentials for another user. Then we used the runners to switch to that user, actually the run as cease program. And this user had the SE-debug privilege, so we used that to inject into a privileged process and tell it to launch a binary for us. And then we got system, we found the private key, and here we are. So let's do a quick sessions here again. We have two sessions, one as Ashleigh and one as system. We could also have gotten one as dev, but it's not really required anymore. And we still have our beacon here as system. The other one is red, so maybe it died. It's not really always the case though. As you see, if we do it again, it just called back. So they are both still alive. Red doesn't always necessarily mean it's dead, just that it hasn't responded in a while. So that's it for today. Thank you for watching. Feel free to join the Discord and reach out if you have any questions or want to try out the lab. Yeah, that's it from my side, and see you next time.